All right, we are going to be looking at how do constructive and destructive natural processes change Earth over time, and what evidence supports the theory of continental drift. Now, through this learning experience, we're going to cover three main objectives, and that's E.8.9A.2, 3, and 4. So we're going to be looking at the theories of plate tectonics and debating them. We're going to be looking at how the maps of land and water patterns from various time periods, rocks and fossils are going to show evidence that plates have moved great distances, collided, and split apart. And then you're going to have to research some scientific ideas on the constructive and destructive process and how they have changed over time. Okay, so the first thing we're going to do is watch a video, and well, two videos to be exact. So you need a sheet of paper, and you're going to write these two questions down. What did Wegener find that he believed was evidence to support his theory? And then the second question is, what did scientists find by using echo signals along the ocean floor? So I'll give you a minute to write those down. And if your teacher needs to pause the video, she can.
Alfred Wegener was a German meteorologist who had a few risky hobbies. He loved hot air balloons and even proposed to his girlfriend in one. Wegener was the kind of guy who couldn't sit still. That's partly why he gave up astronomy, the field he was trained in. One science was just not enough. To learn more about the Earth, he read any scientific paper he could get his hands on. Wegener was looking over an atlas when he noticed something curious.
Wegener later told this story himself. He said, I started looking at it, and it was really odd. He said, I'd always noticed that Africa and South America fit together. He said, but this map had information from deep down in the Atlantic Ocean. And what it showed is that that match between South America and Africa goes all the way along the continental shelf, all the way down to the foot of Africa. Now, if this is the case, he said, he thought immediately and pointed it out to his office mate, this isn't just an accident of sea level that these things look alike. These things look alike because they're connected in some way.
Almost for fun, Wegener developed an idea that the continents were once connected and drifted apart over time.
Wegener's original idea about continental drift was a momentary intuition. For it to get to be science, you have to make the idea real.
In 2 years, he had found his evidence. A first clue was the Mesosaurus. Fossils of this prehistoric reptile had been found in both Brazil and South Africa. It was, Wegener said, too small to have swum 5,000 miles across the Atlantic. He found a second clue in the Karoo Desert in South Africa. Here, massive glaciers had left giant scars and scrapes on the rocks. It didn't make sense. Glaciers in burning hot deserts? And what about the coal deposits found on the Arctic islands of Spitsbergen? Geologists knew that coal formed only in tropical forests. To other scientists, it was all a big mystery. To Wegener, these clues were the building blocks of a really radical theory. He proposed that all the continents were once joined in a giant supercontinent. He named it Pangaea. He published his theory of continental drift. This should have made him famous. Instead, he was bitterly criticized by leading geologists.
Many of them said disparagingly this was a theory of the Earth proposed by a weatherman, who moved continents around the way clouds move, but the Earth is this big solid thing. Continents don't just get up and skate around like pats of hot butter on a skillet.
Geologists had a completely different idea.
In the late 19th century, most geologists subscribed to a theory they called contraction theory. This was the idea that early in Earth history, the Earth was an incandescent globe of hot gases. Then, over geological time, as the Earth cooled, it continued to contract. And as it contracted, this crust collapsed. But the whole thing doesn't fall at once. Pieces of it fall first and then other pieces. And that's more or less how geologists imagine the Earth.
Wegener didn't buy this theory. He was sure he was on the right track and passionately defended continental drift. Although he educated himself well in geology, Wegener was still considered an outsider to the field. And there was one crucial weakness to his theory. How did the continents actually move? This he could not explain or prove.
So let's go
Wegener
back
didn't know what made the continents
to
move.
And
frankly, I don't think he thought that was his
our question,
problem.
our big question that we were looking at. And so our big question, when we look at it,
Wegener would wait for the
it said, what did Wegener find that he believed was evidence to support his theory? And so according to our video, we found several things, right? So we said, what was the first thing that they said when he looked at the map? He noticed something. What did he notice? Right, Kendall? He noticed that that Africa and South America fit together. Okay, he said that they fit together, and he said that there was other things that show that they fit together, and it had to do with the material that was found along the coastlines. And he said they fit together. They had to be together. And what else did he say was evidence that is going to support this theory that South America and Africa not only fit together, they had something else in common? What was that thing that was discovered? The fossils, right. So he discovered that the Mesosaurus fossil was in Africa, in South Africa, but it was also in Brazil, which is in South America, and that was a small organism. And he was like, there's no way that this tiny organism swam from South Africa to South America. There was no way that mass body of water they could have survived. So he said that's evidence to say that they once were together. What other evidence is he saying is kind of odd? It doesn't make sense if the plates weren't together. Yeah, the scars from the glaciers. So he's saying, why would there be scars from glaciers on rocks in the middle of the desert? Like, what? That doesn't make any sense. He's saying that they had to have been together, and at one point that was a cold environment where there was glaciers. And so that's furthermore is evidence. And then he also said one other thing about the evidence. Yeah, he said the coal deposits. He said geologists know this. Geologists know that coal deposits are made from forest areas. And those coal deposits had to have been once was a beautiful forest. So he said this is all evidence. So now we need to find what scientists discover on the ocean floor. Let's check that out. So that's going to be our further evidence. So plate tectonics, further evidence. What further evidence do we have? Okay, now we're still missing some components here that explain how the plates actually move. This video is not very long. It's about 2 minutes.
During World War II, scientists at sea were using sophisticated echo technology to track submarines when they turned up surprising information about the ocean floor. There they found a stretch of underwater ridges made of continually erupting volcanoes.
The mid-ocean ridges formed when molten rock rises from inside the Earth and then pushes the crust apart.
A vast spreading seafloor strong enough to move the continents. Not only is new crust formed at mid-ocean ridges, but it dips back down again into the interior of the Earth.
You put this all together, and what you get is plate tectonics. The idea that the Earth's crust can be broken up into large pieces or plates that consist of both continents and also pieces of oceanic crust moving together over the face of the Earth.
When two plates collide, sometimes one is pushed downward and melts into magma. Eventually, this red-hot material rises to the surface and explodes, creating a volcano. So new crust is born at mid-ocean ridges and destroyed at deep ocean trenches, like a never-ending conveyor belt. And two plates simply nudging each other can cause catastrophic results, like when the San Andreas Fault slipped in 1906. How fast do the plates move? If you live in the U.S., you're probably standing on the North American plate. In the course of 1 year,
let's go back to that
the ground under
question.
your
So
feet
we
will
got
move
some
up.
more information, okay? So what did scientists find by using the echo signals along the ocean floor? So in World War II, they developed new echo technology, and when they used that echo technology, they just made some discoveries. What did they discover? Okay, so they discovered underwater volcanoes. Thank you, Leland. And that those underwater volcanoes were making new land. It was making new land. And it was vast spreading seafloor. The seafloor was spreading. So if you remember when we were talking about our plate tectonics, spreading apart, dividing is our divergent boundary with our mid-ocean ridges. And then we have what's happening as they're pulling apart in one section, what's happening in another section. Yeah, the land's being destroyed. Okay, so like the land is going back into the mantle. So those discoveries help develop this plate tectonic theory. So we need all of these pieces. So this is just touching what's going on with our plate tectonic theory. So you have a job. You're going to prove the plate tectonic theory with evidence. So you're going to piece together your evidence. And so, depending on the resources that you have, there are different resources that your teacher can use to help you develop these. So you can either do the case of Alfred Wegener, and you can use the USGS fossil and mountain chain evidence. And so here you're going to have to label the continents, you're going to have to color the fossil mountains, you're going to have to cut, and you're going to have to piece your evidence together. You're going to have to match it, okay? A lot of stuff here, okay? And so you're going to have to piece all of this evidence together to make a map, okay? And then answer some questions that go with that and prove this theory. Now, if you don't have that, if your school has STEM scopes, then you have a different document that you can use to put together, but you're going to have to piece these pieces together. And you can see that we have coal beds, we have deposits, we have fossils. So we're looking at rocks, we're looking at fossils, we're looking at the shape, we're looking at coal deposits, we're looking at all these pieces of evidence. And then while you're putting this together and you're doing some research, you need to find out what is missing to make this a solid theory. There's one piece that's a solid piece that's missing.